2 days ago was Sunday. Okay, that's what I'm saying.
No. Did you realize you got the hours and the application?
I did. Really?
We haven't done it.
Nothing yet. What did you do with her eye? She drug off. Yeah, I got the notes for you. And we did the other law in practice, and we had a lab that wasn't graded.
Okay. Tell me one of the gas laws and give me something about it. Give me one of the gas laws first.
Charles.
Okay, give me something about Charles' law.
It's division.
It's division, okay?
You cross multiply.
Okay, stop. You're doing good. Stop.
Oh.
May not have to necessarily be cross multiplication, but you can do it. How you do the math up to you, Ava.
Boyle's law is pressure times volume equals pressure 2 times volume 2.
Okay?
Would you have
You're
a
two.
break? Yeah, I can do it.
What? You got 4 gas laws, and all I want is one thing about them. One thing about them. You're not getting out without telling me something.
Wait, which ones are those?
Anyone. You can tell me.
No, the ones.
You can go back to Boyle's law and tell me something else about it. You can go back to Charles' law and tell me
What?
something else about it.
What's going on with this brick?
Well, you unplug it because that's how it charges. No, you unplug it from the brick, and then you take the extra cord. There you go. There we go. So, okay.
Boyle's law, like the volume increases the pressure decreases.
Very good. So Boyle's law, the volume increases, the pressure decreases. Good. That's the kind of stuff I want. Good. Give me something else about Boyle's law. Hold on. Back to Boyle. Let's boil this through. What else about Boyle's law? Give me something.
The temperature and the N are constant.
Okay, temperature and amount of gas are held constant. Okay? What would a graph of Boyle's law look like? Yep, Boyle's law.
Constant.
Really? Temperature goes up in Boyle's law?
No. Temperature is constant.
I'm just trying to get you ready for your quiz Friday, ladies and gentlemen.
Okay.
So somebody
You
tell
should
me
have been on the
about
board.
what?
You should have written that on the board.
Why? It's only Tuesday.
So we know, so we can study for it.
You're right. I wish somebody would tell you when
No,
the
I mean
quiz
up
was.
there.
On the board.
I meant the whiteboard.
What color is that board?
On the whiteboard that says chemistry.
Okay. But that whiteboard also says conceptual chemistry.
On that side. In the black square where it says chemistry in blue.
Wow, we're finally starting to pay attention to some of those things that I put up there. Okay, so let's go back to Boyle's law, ladies and gentlemen. What does a graph of Boyle's law look like? Okay, good. Now tell me what that graph would look like since they just told you the relationships. No, a graph. A graph is a line. What would the line look like on the graph? If it is an inverse and a constant, and a what? Inverse and a what? No.
That's what I said.
The graph of Boyle's law is not an inverse and a constant. The graph of Boyle's law is an inverse and a non-constant, which would look like what again? A line curving up. You're half right. Try again.
It almost curves up. Like
A straight line curving up. That might be my favorite one of the day, ladies and gentlemen. Can someone go to the board and draw me a straight line curving up? Come on, think.
A straight line going up.
Okay, that is possible. A straight line going up. Austin, is he right?
It depends which way the numbers are going.
No, it doesn't. A line of pressure versus volume will always have what shape to it? A curved one going down. Why? Because Boyle's law, Kiana, is a what kind of relationship?
Inverse.
And Cynthia, what? What is the other kind of relationship? An inverse and a non-constant. Non-constant. Now we did manipulate Boyle's law to make a constant, but to do that we had to do the what of the pressure?
Reciprocal.
The reciprocal, the inverse of it. The reciprocal or the inverse. Then we did get a straight line, constant relationship, going upward, direct relationship. Okay, let's go back to Charles. So what are the variables involved in Charles' law, Mitzi? What are the variables involved in Charles' law? Give me one of them. Temperature, good. Give me another one, Jennifer. Not in Charles' law. So it's not temperature, or it is temperature. It isn't pressure, so what else would it be? Yeah. I gave Farhan like 5 chances to redeem himself. I got to give you at least one. Volume. Volume and temperature are the variables. So what is a constant, Rose, in Charles' law? Okay. You guys are killing yourselves right now because you're not listening to each other. There are 4 factors that affect the gas: volume, temperature, pressure, amount of gas. There are 2 kinds of relationships, inverse and direct. Inverse relationship, the 2 variables that are changing, which is why they are called variables, is because they are actually changing, are going in opposite directions. That is Boyle's law. The volume goes up because the pressure went down, or the pressure went down because the volume went up. I don't care how you want to say it. Now, in a direct relationship, both variables are going to go in the same direction. They are both going to increase or they are both going to decrease. If you are not a variable, then you are a constant. Now, Mitzi told us that temperature was a variable in Charles' law. Jennifer then said that volume was a variable in Charles' law. So what is a constant in Charles' law? What? Well, if volume is a variable, it can't also be a constant, because a variable means that it changes and a constant means that it doesn't. So volume and temperature are the variables. What are the constants? One of them. The 4 things that affect the gas. Very good. Pressure is therefore a constant. It is something that does not change. Olivia, what is the other constant in Charles' law? Very good. Amount of gas. Those 4 things in a gas law are either variables or constants. And every gas law we have given you so far has had how many variables, Olivia? 2. Which means how many things are held constant, Farhan? Were you not listening? Okay, at least I can accept that. So that what you're doing on your computer, the game or whatever you're doing is more important than going over this. I understand. Okay, I got it. Okay? So, Isaiah, if there are 2 variables in every law that we have talked about, how many constants are there? 2, because there's only 4 things in there. There are only 4 things in there. Okay? So now, Charles' law, volume and temperature changing, pressure and amount of gas are held constant. What kind of relationship is Charles' law, Aiden? Inverse or direct? No. Try again. Good. Direct means if one thing goes up, the other goes up. What kind of mathematics is done to the variables in Charles' law? Rocio. Addition, subtraction, multiplication, or division? No, not in Boyle's law, yes. In Charles' law, it is division. Whenever you have division, that means you have a direct relationship. That means that the line on a graph is going to go in what direction, Lizette, if it is a direct relationship? It is going to go up. And if it is a constant relationship, Yuritsi, if it is a constant relationship, the line will not only go up because it's direct, but it will also be straight. Thank you. All these things go together, ladies and gentlemen. All these things go together. Okay? Now, Ifra, yesterday we also covered Gay-Lussac's law. Can you give me either a variable or a constant from Gay-Lussac's law? Is a constant or a variable? Because I said you could give me either one. No. Volume is not a variable in Gay-Lussac's law. Therefore, it is a constant. Now, can someone give me the other constant in Gay-Lussac's law? The other constant. What? Very good. Amount of gas. So now we got volume and amount of gas constant. Angel, give me a variable then. A variable. Volume and amount of gas are constant. Give me a variable.
Pressure?
Thank you. Pressure. Pressure is therefore a variable. What is the other variable, Jasmine? Temperature. Of the four things that we have been talking about since the start of this unit, they are either going to be variables or they are going to be constants. Variable means they will change. Constant means they won't. What kind of relationship is there between the variables in Gay-Lussac's law, Cynthia? Inverse or direct?
Direct.
They are in a direct relationship, meaning they are both going up or they are both going down. What kind of relationship is it, constant or non-constant, Olivia? It is a constant relationship. Means they are going in a straight line, ladies and gentlemen. Okay? Means they are going in a straight line. KP, mathematically, what will we do to the variables because of that? In Gay-Lussac's law, we will divide them. So whenever you see two variables and they are being divided, that tells you that they are in a direct relationship, ladies and gentlemen. That is what that means. Okay? Questions? Okay. Today, you're going to do a lab activity. And I want you to keep four things in mind. Pressure, temperature, volume, and amount of gas. Now, because the experiment we are doing is not directly related to a single gas law, during the experiment, I am going to ask you what happens to each of these things. Now, there are only three options of what can happen to these things. What's one option, Alexis?
Wait, what was the question?
For these four variables, in any activity, in any lab we do, there are only three options for what they can do. Give me one of them.
Go up.
Go up. Give me a second one. Aiden. These three variables. For these four variables, in an experiment, in a problem, in a question, can only do three things. Alexis said they could go up. What else could they do? They could go down. Ava, what is the third thing they could do? Remain constant. So when you are doing your activity today, you need to think about, is pressure going up or down? Or is it staying constant? Is volume going up or down? Or is it staying constant? Is temperature going up or down? Or is it staying constant? Is amount of gas going up or down or staying constant? And by the way, we are talking about gases. I don't care about liquids. I don't care about solids. These are not solids laws. These are not liquids laws. These are gas laws. So the only thing we're worried about is gases in this unit. Questions? Okay, good. Open up your computer and get to the implosion lab, ladies and gentlemen. Okay. So, using gas laws to explain the interaction between pressure, temperature, volume, and amount of gas that explains the results of this lab. That is what you are going to be doing. You are going to use gas laws to explain what happens in this lab. So, here's what you're going to do. You are going to get an empty soda can out of the box in the back right there. By the way, you may work with up to 4 people, but each person does their own can. So you're going to get your can. Please change where it says 1 to 2 milliliters of water. Please change that to 15 milliliters of water. And it is about 15. I accidentally poured 17 milliliters in here. Close enough. I'm going to add it to my can. You'll then take your can, and you can fit 4 cans on a hot plate, ladies and gentlemen. That's why one of the hot plates at each station is pulled forward. Just use that one. There is no need to use one hot plate on one side and one on another, because there is plenty of room on the hot plate for up to 4 cans, and that's how many people can fit at a lab station anyway. You're going to place the can on the hot plate until you can see steam coming out of it for about a minute or 2. Now, this is the first spot where you are going to have to not only make observations, but determine what is happening to all 4 of these things for the gases inside the can. Inside the can. What is happening to their pressure? What is happening to their temperature? What is happening to their volume? And what is happening to the amount of gas inside there? You are going to have to specifically in the conclusion say, this did this at this time. This went up, down, or stayed constant. This went up, down, or stayed constant. Now, you will also have to take observations of the water before you begin, 3 to 4. Okay, if you don't have at least 3 here, you don't get your point. You'll have to take observations of the water in the boiling can, which is very difficult to do since you can't see it because it is inside a can. However, observations do not just rely on our sight. They rely on what we feel, what we hear, what we smell. Please do not taste anything in this lab. And maybe you will see something going on with the water inside that can. But you only need 3 things there, ladies and gentlemen. Okay? At your station, there is a bucket filled with ice water. We can't use snow and water because there's no snow outside. So we have them filled with ice water. After this has been boiling for a minute or 2, ladies and gentlemen, you will take 1 set of hot hands. You will grab your can, and as quickly as you can, you will take it and you will invert it into the container full of ice water. Invert means turning over and placing under the surface of the water. And hold it there until something happens. If you take it off and you stare at it and you look at it and you get a good observation of it, the experiment will not go as well as you had hoped. So you grab it, you turn it over, you put it under the surface, and then you make observations of what happens to the can at that point. Questions, ladies and gentlemen? So When the can is placed in the cold water, you will again make 3 observations. There is room for 4 here. There is a minimum of 3 required. You will then, ladies and gentlemen, answer 3 questions. Why did we heat the water in the can? And again, all of these questions should be framed around what?
The laws. Gas.
Around gases. What did heating the water in the can do to the gases inside? Why did we put it in an ice water bath? What did that do to the gases inside? And then why is it important to turn the can over when placing it in the ice water bath? What did that do? Why was that important? Then, ladies and gentlemen, you will write a simple conclusion. Your conclusion will say what caused the can to happen to what it happened to do what it did. What happened to the 4 variables when you were heating it? These are the 4 variables. What happened to these 4 variables? Well, it was in an ice bath, ladies and gentlemen. Questions? There are 24 stations in the back. There are 20 of you. There are cans in the boxes there. There are hot hands at every station. There are everything you need. Go to work, ladies and gentlemen. Go to work, go to work, go to work. By the way, ladies and gentlemen, I'm telling you right now, my money is on Cynthia. I'll tell you after it happens.
Well, that doesn't sound good.
You're one of my candidates too, just so you know. Excuse me, guys. I need one of these.
Makes me Someone's going, but I hit
So just use this one. Just use this one. You only need one. There you go. You need cans for each person. Exactly what I just explained to you. Yes, each person has their own can. Cans are in the box right there. You're welcome. We're still working together.
What? Who are you guys playing for soccer? Today? Yeah. Is it a team game? All 3 of us are playing team game.
I wanna go. I did train last night, but somebody like opened and shut off my Mini Cooper, went in, stole the back seats, and stole my reverse thingy, like my stick, and then I was like watching my car everywhere I went because of it. I was so paranoid.
Like 10?
That's too much.
And then I drove into a ditch and somehow I got out. I was just being
Get your water heating. When you turn your hot plate on, make sure you are turning the heat on and not the stir. You will be here forever waiting for it to heat up. Turn your heat all the way to 10, and then please remember, when you turn the hot plate on to 10, the surface gets to about 500 degrees Celsius. Plenty hot enough to burn anyone who touches it, or any computer that is in contact with it. This water. Water that you're putting into the can. Yep, the water that you're putting into the can. That's always the water, the stuff that we're drinking. Now, water is water. The observation you're making with this would probably be the same as what you're making there. Bumpy is water.
It's called a good observation,
But
like
that's
it's
not
not
water.
moving. How do I say
Wow, that could be an observation, right? Can you see through it? That means it's transparent. Clear is a color. Transparent means you can see through it and light can pass through it. The top, if the light is on the top. Now you're just waiting. We're good.
I haven't tried to run on it yet.
I've taken the track out off 3 times already.
Lisa said no running, but I kind of thought. Well, and I'm left-footed, so it's not like I use my right. The only thing I do is try to
The
only thing I do is trap my right.
my body is so
Coach was trying to show me the
I don't know how I
the air yesterday. I can't do it because I'm so used to having.
Oh, it smells. Take you put no odor. There's definitely a burning odor.
Okay.
For this experiment, it doesn't have to be.
Well, yeah, I'm so odor.
Yeah. I rolled it right
No,
now.
glass did not make a person. They may make a person spiritual, not linked to the class.
I'm gonna take hella ibuprofen before practice tomorrow.
You need any biofreeze?
No, I can always still some.
No. You always know I got a lot of biofreeze. I'm not even doing anything. But it was to the point where, at the beginning of the year in gym, I felt this muscle in my stomach. I don't know how I did it, but I did it.
I remember on halftime, I was like, on Friday. Shirley took me down in here and we're all smelling Shirley's father, not me shit. What was prayer and quad.
I'm the one here.
I don't know why.
Because this is way.
Oh, that shit.
People work with you get enemies, you're exposed to
I'm really cold right now. That's where my parka is. No, that's in my car. Same with my crutches. My crutches are in the car. I have to give them back to the Same with the ace wraps that she gives us. We can wash those and give them back. Do they reuse the horseshoes too?
I remember that one time where, I think you left your toes or something, and there was 5 people outside the room, and you had to pick up some of your toes.
Yeah.
Oh,
You keep yourself a lot.
It's just I have a bad
Why would you not use the hot
You
ones?
think it's better to grab it like this?
Oopsies. Were you paying attention when I was doing it up there?
Oh,
Okay, then that kind of's gotta stop. It's gotta be yes. Okay, do it again, doesn't happen. Too late, too slow. Cynthia, congratulations, that was wrong. Are you done?
Wait, so it's because of the pressure that it made me pop?
All the questions, yes, that's usually like this.
I think so.
They're now cool, yeah. By the way, don't forget, when you are done, ladies and gentlemen, when you are done, your cans that you use go on this cart, ladies and gentlemen, right here on this cart.
That's scary.
Turn your hot plate off when you're done, leave your bucket of ice there, and just put the cans on that cart.
Some people
By the way, try not to get your computer soaking wet.
That's not mine. I'll be fine.
Wipe up any water that is left on the counters.
I can pop, popping sound. Like a shape, I mean.
Again, on that cart right there.
What were you wrong about?
I'll tell you.
I tried to feel first, not you.
No, that was not what that was.
Well, that's what happened.
It was, but that wasn't what I was betting on. I'll tell you what I was betting on.
We used an ice water bath, so this is temperature.
How would you know it's going?
Why did we keep the can?
I think we heated the can so it's either a temperature thing or a.
To increase the temperature.
I feel like it's maybe a little pressure thing, but.
Raising the
We used an ice water bath so the temperature changed and the volume. I hate that. And turn some of the water into water like that. Turn the water into
I put to increase the temperature of the gas can.
I looked it up and it said so. So probably it's water.
There's no gas in it.
The water vapor that it made.
The water vapor is not said.
And gas.
You did good. You have to put some more in from it again. Take another shot.
Like yeah, I was scared.
One at a time. Go ahead. Who's gonna go first? You can. That was what I was betting Cynthia would do.
What happened?
Scream. There's always at least 1 to 2 screamers in a class. I was betting on Cynthia doing it. You scream because someone else screamed. So Cynthia, I am impressed. You surprised me. Again, only
He's your
one.
biggest hater, I swear. What is Brazil?
The cold water will pull any remaining gas molecules to increase their kinetic energy and therefore
Remember, everything in your lab is about gases. And what will happen to gases if you make certain changes?
So the pressure.
So I will to the second one, we're using ice water bath.
I'm sorry. I don't know.
I don't think it's there.
Because like
Gas goes up, so when you look it up, I had nowhere to
That and that do not look anything alike. Okay, please this is
Here,
back.
I found the answers.
what is the pressure?
Are you on the second one or the first one? We used an ice water bath so the pressure decreases inside the can. Since the air pressure outside the can is stronger than inside the can, it causes the can to go up.
So like the pressure.
It decreases inside the can, and the pressure outside the can is stronger, so it causes the can to go up. Does that make
No one
sense?
has ever died from this lab yet. Okay, then I don't know what to worry about. There you go. Come around to this side where you can.
Hey, Angel. Guess what? I have all the answers.
Okay.
Why is it important to turn the can over when placing it in the ice water? So the same reason that we're using ice water? What is it? No.
So then, because we put it up in the warm gas when it's outside, it's strong water.
Because gas
Let's actually
yeah.
use those lines.
Group who was here, I got some water to clean up
I
the
think we
red
keep
station.
So to the gas.
Isaiah, you got a can to clean up at your lab station?
Well, we were
Yeah.
tracking because they had nowhere to go.
Yeah, I'm gonna put to trap it.
To trap the gas.
The volume.
Guess what?
I don't know. Is that why?
If we did it just facing upward,
Why do we do
Exactly.
an ice water bath?
Here's the thing about gas laws. Anywhere? All.
Okay, so she's
Laws.
for 9, 10.
I'm just joking about it.
That eat.
Laws.
Which allows adults. Yeah.
On these parklands.
It cools down.
Again, ladies and gentlemen, in this activity, you're thinking in terms of the gases. The gases inside the can. First of all, big question, what caused the can to crush? That is the first thing you have to determine. Give you a hint, it is one of these 4 that caused the can to crush. You have to tell me what caused it and how that happened. Yes.
We have to use all 4 variables
When you're doing this and this, yes. You have to tell me what's happening to each one of the 4 when you are heating it, and then each one of the 4 when you put it in the ice water bath.
Do you want us to write the conclusion in one paragraph or just
No,
answer
you
those?
can, because of the way it is set up, you can answer this question. Then you can go through and you can tell me what is happening to these variables. Okay? What is happening to the variables?
We haven't done those 2 yet.
What caused the can to crush? If I wrote pressure, would that be wrong?
More specific. There's pressure all the time. Why did the can actually crush? There had to be something that was different inside and outside.
I don't know. Just random.
Okay, turn it in blank. It makes it easier for me to grade.
You're so mean.
Well, what would you like me to do? What would you like me to tell you? You said you gave up. Okay, turn it in blank.
If I wrote more pressure, would that be wrong?
What?
If I wrote an increase in pressure, would that be wrong?
Increase in pressure where?
In the can.
Okay, I want you to think about this, ladies and gentlemen. What is this lab called?
Implosion lab.
Okay, what is the difference between an implosion and an explosion?
Implodes, goes like boop, and then explodes, it goes like boop.
Explosion goes outward, implosion goes inward.
So
Now, as sad as this is to say, ladies and gentlemen, last summer there were 3 people who experienced a major implosion.
wasn't it like 4 or something?
Was it 4? I thought it was 3.
5. I thought it was 5.
The whole
I-
group.
There was a ton of them because it was.
No, I thought it was a father, his son, and then the guy who owned the submarine.
How many people were
Anyway.
on the sub?
But
There
there's
was-
5 of them. 'Cause there's
Was
just
it?
5
There's
guys.
5.
Was there
yeah.
5? Okay, thank you. 5. An implosion is when you go inward. Okay? An explosion is when you go outward. Well, the question really becomes, your can imploded. What caused your can to implode? What was different inside the can? And I'm not looking for you to give me an answer. I'm looking for you to write it down on yours. Tell me what happened. And then with the variables, you need to explain how we created that situation, basically. Yes.
Turn to the back.
Are you all done?
Yes.
Completely? Your lab is turned in?
I'm not turned in yet, but I can turn it in.
Turn it in, and then you can go.
Wait, I'm so confused. So we put the can in the water, and because there were different textures, it went inwards.
So you think the temperatures caused that? And I'm just asking.
I don't know. I'm asking.
Well, okay.
Stronger
But think about it.
when
Why didn't we just set the can on the hot plate, heat it up, and throw it into a cold thing of water? Would it have imploded? Has anything ever heated up and cooled down and imploded before? Then it probably isn't temperature. Temperature probably had something to do with creating the situation that allowed it to implode. Yes.
For when it says variables while heating, would we technically have to say that the amount of gas changed because of the hole in the top of the can?
Not only that, but what were you doing while it was heating?
Waiting.
What?
Waiting.
Waiting, okay? Eventually, when it was heating, how did you know when it was kind of ready to go?
It was steaming. It created the gas at the same time.
What?
It was creating the gas at the same time.
Water was a liquid, but the steam that came out was a gas. You tell me, does that change the amount of gas inside there?
Wait.
I'm waiting. Now, if you create more gas inside that can, what else does that do? What if you created less gas inside that can? What would that do to some of the other variables? Right? So we can't change one thing without other things adjusting. So yes, we heated it up. We know what happened to temperature while it was heating. At least I would hope the gas would have done what? I would hope it would have gotten warmer, right? So, okay, what does a warmer gas do to pressure, do to volume, do to the amount of gas inside there? These are the things that you need to think about as you're writing up what happened. But the first thing is, figure out why you think the can crushed. Which of these four things do you think caused the can to crush? And by the way, I did the opposite in class. I did an explosion for you inside the glass jar with the balloon inside it. When the balloon got bigger and bigger and finally exploded.
I'm so hungry. What?
I'm just enjoying watching you guys think. I really am. I wish you would do more discussing with each other. Bouncing ideas off each other, because that's how problems get solved. But again, you want to go it on your own, you're welcome to.
Yeah, shrink or get bigger and heat. Get bigger. Never mind. Oh wait, okay. So we heat up the gas, right? When we put it in the ice water, the gas went down because of the heat. So then the can had to fill up the space because of the volume.
Mr. Moran, if I wrote
Yeah.
the amount of gas increased so the pressure decreased so the pressure around it was greater than the pressure in the can, is that right?
Could be.
When we heated the can.
What happens if I tell you no?
Well then, I'll change the answer.
Okay, so it's like on a test. You come up and you go, Mr. Brand, is this the right answer? Can I tell you yes or no?
Yeah.
Well, no.
Well, what happens if I tell you no?
Then I change it.
What happens if I tell you yes?
We keep it.
So what's the sense of me giving you a test to see what you know if all you're going to do is ask me a question if it's right or wrong and then change it depending on my answer back to you?
I just don't want to get it wrong.
Have you ever gotten anything wrong before?
Yes.
Okay, are you dead from it?
No.
Okay, you'll survive this too. Are you done? Okay. Cynthia, what?
You're talking so loud I can't think.
I'm just gonna write that.
Can you
Cynthia, I have bad news for you. This is the lowest volume I'm probably ever going to have in this class.
Were you told a lot as a kid that you talked too loud? Like, were you yelled at by your parents for that?
I don't
Were
think
they
so.
like, "Gosh, Christopher, you're just so loud. You talk so loud." They never said that to you? That's shocking, actually.
That makes it.
Your parents, like, were your parents loud people too?
My parents loud people? No, I don't think so.
No, you don't think so?
Why are you loud?
Are you exactly like your parents?
No.
Okay.
But I'm not saying
Wait.
anything about your parents. I'm not saying
Doesn't make
why are
sense,
you
though.
loud. Like I'm asking you. I'm not asking about your parents.
Don't feel that I am, other than when I come in and greet you in the morning or the afternoon.
Is that how you like wake up every Saturday and Sunday and just
Imploded.
scream that?
Yes, I go up to my kids' room Saturday morning and I go, good! Yeah, my kids love me.
Okay.
Can you remind us what happens?
I will when you turn it in, yes.
No, you like.
I will go ask Miss Shinar.
Okay, what's gonna happen after I read it? What are you gonna ask me?
You can be like, no, this is wrong.
Okay, and then you're gonna do what?
Or you could be like, you can add more to that.
You can do it as a whole class if you want. I never said you couldn't, but everybody's doing things individually. But again, I asked you to bounce ideas off of each other. Do it how you want and turn it in. Do it how you want to turn it in. But I'm not going to look at it and go, nope, that's wrong. Because you're going to redo it. I want your idea of what happened. If you're done and it's turned in, yeah.
How do you spell imploded?
IMPLODED.
Okay, thank you.
You're welcome.
Okay, I like that definition for from what you said. And it makes more sense. I didn't even so the person did.
Yes. The pressure decrease, but it because
So
molecules
I feel like
stop moving.
volume stayed the same. That's why it imploded because it needed to keep the same. Oh wait, no, it went down. Wait, this is hard.
What is it?
Wait, can you tell me if any of them stayed constant? You know?
I will tell you this. Yes, there were points where some of them held constant.
Oh, wow, okay. While heating, the volume stayed the same. No.
Well, remember, we're talking about where.
No, because Sophia, he said that.
Hold on. We're talking about where
What?
for the gas.
In the can?
In the can.
But you just said that more gas is being created. Would that not mean that they pick up like that?
But then it's
There's
also
more.
released.
But what is there at the top of the can?
Okay, so the volume system.
So we're talking about the volume of the can, right? The gas is inside the can. Think about that. Did that change when you were heating it?
No.
No, it's just.
Again, I'm just asking you that question. Did the volume of the can change when you flipped it over and put it in the ice water bath? Most definitely. Right? So there are times where things could stay constant. What's inside here, ladies and gentlemen?
Air.
A gas. Okay? A gas.
Oh.
When I release the gas, does that change the volume? Can's still the same size. Got it?
Yeah. Is it cold? Yeah, it's okay. Yeah, it's the same. It's the same.
Really?
Yes. It feels the same. Did it change?
No, it didn't.
You have no feeling in your hands, do you?
No, I don't.
Is it cold now?
Is it cold? Yeah. What temperature was it originally? Room temperature. So what did the temperature do in here?
Go up. Don't go down. It went down. It went down.
Thank you. Thank you. It went down. What did we change?
The pressure?
Of gas.
Okay, we changed the amount of gas. Probably changed the what as well? The pressure.
But what
Which one of those, though, would cause temperature to go down?
pressure?
Well, pressure and temperature into what kind of relationship?
Are in direct relationship.
It seems to make sense to me.
As pressure.
Anybody know what temperature and amount of gas kind of relationship they're in?
Also
In
direct?
constant.
Think about this.
No, because that's Avogadro's. Isn't it also constant? Or direct, I mean?
But Avogadro's is about volume and
Oh, yeah, you're right.
amount of gas.
Isn't it all of them combined?
Wait,
That's what we're
Sorry,
doing.
Charles's is
So,
volume and
temperature-
temperature.
Right, but we're not changing volume.
Down.
So let me ask you this.
Pressure goes down.
Okay, pressure. Wait, no, we don't.
Well,
have
slow
pressure.
down. You don't have one, but let's think about this.
Oh, that makes sense.
You said that pressure went down because temperature went down, right?
Okay.
Where is pressure in your formula?
So
Where's temperature?
Okay, what was that?
Bob, where is Avogadro's N in a formula? On the bottom, right next to what other letter if they were all in the same formula? So T and N are what?
Those are inverse then.
Why?
Because those are should be multiplied.
Very good. Now you're starting to put things together.
So then I
So if the amount of gas went down, temperature would go up. So can that can get warmer because the gas is leaving? No. It didn't. It got colder. So what had to cause that change in temperature? The pressure. Volume didn't change. The can is still the same size. The amount of gas did, the pressure did. Pressure says, though, if I'm getting less pressure, temperature should go down. Amount of gas says if I have less gas, temperature should.
go up.
Well, which one did the can do?
It went down.
So what had to cause that?
Pressure, not the amount.
Not the amount. Very good. You could have two things trying to do opposite things to that can.
Wait, so
Which one wins?
that went down in ours because the temperature went up.
No, I didn't say that. That was a whole different situation.
But the amount of gas stayed the same once we put it in the ice bath because the gas had nowhere to go. So
That's a good hit. Wow, good job.
Ah, okay, Pete, good job.
what?
What? Okay, I'm just gonna stick with this answer. I think
I thought it was just
Volume.
You have 5 more minutes, ladies and gentlemen. That is the last of the class time I will give you on this.
Can like 3 of them change?
Mm-hmm.
Yeah. Okay.
Definitely. Definitely.
Okay, well, I'm turning mine on.
Okay.
Wait, how detailed do we need to be for what caused it to crush?
I am looking for you to tell me which of these 4
Okay, just one of the 4,
or
And then-
multiples
and then what the change in it.
and how it caused it to crush.
So the change that. It
So
went
if you're
through.
telling me, okay, let's use this as an example, amount of gas. If that were a sealed container and I could somehow create a lot more gas in there, what would have happened to the can?
Exploded.
That would have exploded. So the can exploded because we created more gas inside there. Boom, burst. So that is the kind of explanation I'm looking for. I don't want you to say pressure. Well, pressure.
Yeah,
What kind? What? How did pressure crush it? How did volume crush it? If you're going to say temperature, because we put it in a cold water bath, how did the cold water actually make the aluminum can go? That's a technical term. Feel free to use it.
How do I write that?
F-U-T-T-T.
Isn't it
Foot.
because, isn't it because the
Hey!
water,
The U silent?
cooled down the molecules inside really fast?
I would guess that cold water would cool something down. Yes. Yes. Good.
Oh my God,
Good.
get out of here.
For like the variables, do we need to have them in full sentences, or can we just write temperature
went down.
and then went down?
I don't need it in a full sentence,
Here's the best.
but you should explain kind of why. What?
Here's the best.
Are you done?
Yes.
Is it turned in?
Sure.
Sure or yes?
Yes. Okay.
So, okay, during heating, would you, okay, this is hard. For the amount of gas, so it was leaving, but then it was still creating more. So would it say the same? Or how would you explain that?
Good question. Well, why was some leaving?
Let's just write we needed more room. So
Okay. But do you think that even by heating it up, that there should be some more in there or not? So I understand some was leaving, and it could leave. But do you think that in there you actually made some more gas because of the water boiling? That would be my question. Okay.
Did we make more gas?
Did you just fart?
No.
Then you didn't make more gas.
Oh.
But you.
But in the lab, you might have.
Did you fart?
No, I didn't fart.
Love it.
I didn't fart.
I mean, that's hard. That's why I
There
asked.
is,
But then you're like,
there is
well,
very
then you
good
make
work
one.
done here, ladies and gentlemen. Some very good work done here.
Okay.
You just love seeing cans being crushed.
The amount of
Well, actually, before you recycle them, you should crush them so they don't take up as much space, right?
That's right.
So you can feel free to do this at home anytime you would like.
That's what I just said. I said we should
No,
do
it
it.
went down.
I feel like a can crusher would be more effective.
I feel like more time and energy efficient, yes, but again, you can do it this way if you really wanted to.
Now, can I just like, can I just put all of my cans into like a big pot of boiling water and then just go with them?
Sure.
Would that do the same effect?
Well, again, I think I mentioned this to somebody. I think it was Lizeth's group. Laws don't work once in a while. It's called a law because it always works. So if you were to do the same experiment at home, I don't care with 1 can or 100 cans. We used to have a pep rally here at school in the fall for football, and one of the science teachers used to take a 55-gallon drum and do the exact same thing to a 55-gallon drum.
Do you want to do that this year?
No, I do not.
Why
But
not?
thank you, because it's too much work.
How do you pick that out? Like, oh.
They didn't. What they did is they had a heater underneath it. They got it to where the water inside was boiling. They put the lid on the can, and then they threw buckets of cold water on it.
So
And
like-
eventually, boom.
So like you're signing up to do that right now.
After it's cold?
Yes, for this year's pep for this school year's pep rally. Yes, for football. Yes.
I'm just gonna write it.
Yes.
If I get it wrong, okay. Can I go to the bathroom?
No, I want to go.
Well, here's the thing. Now we're going back to talking about combined gas laws. So,
Me too.
so
No, but like I already understand it. So can I go to the bathroom?
Yeah.
again, go ahead. Okay? Go ahead. All right, ladies and gentlemen. You have got until the end of the day tomorrow to figure this out and get it turned in. Hopefully you've already done so, but you got till the end of the day tomorrow to figure it out and turn it in, ladies and gentlemen. All right. Open your EISNs up to slide number 43. Now, you want the good news or the bad news?
Good news.
Good news. I am about to make your life incredibly easier.
Incredibly easier.
Incredibly easier. Now, the bad news. We're not going to hold anything constant except for one thing.
Why?
Because it's more practical. You could not hold 2 things constant in the lab that we just did. They're changing. Matter of fact, you had a hard time holding anything constant. So in reality, in the real world, you don't always get to hold 2 things constant and play with only 2 variables. Guess what one thing we're still going to hold constant? Come on. You should know it. It's the same thing you've been holding constant in every other one.
Volume.
Nope. Volume changes in Boyle's law. Volume changes in Charles' law. Amount of?
Gas.
You got it. So we are going to talk about what is called combined gas laws, ladies and gentlemen. Combined gas laws is what you use when you do not hold anything constant except for amount of gas. Now, here's the good news, ladies and gentlemen. The 3 individual gas laws that we have been talking about still hold true even in combined gas laws. Meaning, volume and temperature are in a direct relationship even in combined gas laws. Pressure and temperature are in a direct relationship even in combined gas laws. And pressure and volume are in an inverse relationship. So someone tell me what combined gas law looks like. Formula-wise. Think about it. Where have we always put pressure?
On top.
Where have we always put volume?
On top.
So tell me what the formula would look like. Go.
P1 times V1 divided by T1 equals P2 times V2 divided by T2.
We're not going to change that. We're not going to change that. Here is combined gas laws. Pressure times volume divided by temperature. Guess what? Still equals a constant. Still equals a constant. The only thing we're holding solid, constant, is the amount of gas. So yes, we can do P1, V1 equal over T1 equals P2, V2 over T2. Now, ladies and gentlemen, now for the part that you're either going to love me about or hate me about. P1, P2, V1, V2. This is combined gas laws. If we change the pressure, the volume, and the temperature, we can put all the conditions in on one side and we could still put all the conditions in on the other. Now, in an equation like this, how many things can I be missing and still solve for it? One. That doesn't change. I can only be missing one thing over here. So you have to tell me what the pressure is. You have to tell me what the new pressure is. You have to tell me what the volume is. You have to tell me what the new volume is. You have to tell me what the original temperature was. Then I can solve for T2. By the way, temperature must be in Kelvin. Can't work it otherwise. Can't work it otherwise. Okay? But
Is N always lowercase?
yes.
Okay.
In this problem, if you were given a problem in math, this side of the equation equals this side of the equation. X plus y divided by 7 equals 3x plus 4y divided by 7. What's the first thing you would do with that?
Multiply by 7.
I wouldn't.
Oh.
I wouldn't. If I'm doing the same thing to both sides of an equation,
Yeah.
just going to get rid.
Multiply by 7. It's the same thing.
But you don't even have to multiply by it. You just can get rid of it because if you're doing the same thing on both sides, it'll cancel itself out in the end, right? Now, you may say multiply. I say just cancel it out. Fair enough? Is that a mathematical principle that we basically understand? Yes, no?
Yeah, basically.
Okay, good. So now let's go back a second.
Cancel out the T's.
What happens if T1 and T2 are the same?
You can cancel them.
Hey, guess what you're left with?
PV equal. That's that first one.
That's Boyle's law.
Yeah.
What would happen if pressure didn't change in your problem?
Cancel them out. That's that other one.
There's Charles. And guess what? If volume doesn't change,
That's that
There's
other one.
gay.
don't memorize all three of them. This one takes the place of all of them.
That's gay.
Oh, sorry, guy.
This one takes the place of all of them. If you understand that if something doesn't change of these three, I can just ignore it. You want to put a number in there and multiply both sides by 74.3? Go ahead. I don't care. Isn't going to change your answer if it's the same on both sides. So this one gas law can take the place of the last three that I taught you. The only one it doesn't take the place of is what? Avogadro's. Yes, Alexis.
Why did you teach us all the other ones then?
Why? Because you got to take baby steps before you can run. All right? And now you understand what these laws are. You understand the relationship. I cannot tell you what's going to happen to volume here every time. But if we just have pressure and volume, if this pressure goes up, what's going to happen to that volume?
Go up. Go down. Sorry.
It's got to go down, correct?
Yeah.
It's got to go down, right? Okay. So let's say, ladies and gentlemen, from this side here to this side, pressure goes up. Okay? But temperature goes down. Okay? That can happen. Okay? Pressure going up should cause volume to do what?
Go down.
Temperature going down should cause volume to do what?
Go down. Same thing.
Which one?
Whichever one you like better.
I don't like either better. I like the correct answer better. If the temperature goes down, what happens to volume? It stays the same. Yes, that was which gas law? None. If temperature goes down, what happens to volume? Come on, Charles' law. Goes down. What is the only thing that could happen to volume in this problem? Volume would have to go down. Have to. Okay, it can't. The two variables that affect it are telling it you have to go down. Volume has to go down. But, hang on. That's exactly where I'm going. What would happen if instead we decreased the pressure? What would volume try to do then? But what if temperature still went down? What would volume do?
Go down.
But it can't.
So which one is what's going to happen?
Does it depend
volume
on
It's gonna explode.
your reaction?
Thank you. Now we're back to the tug of war. Now we're back to a tug of war, ladies and gentlemen. Which one is going to happen? Is pressure going to win and say, volume, you go up? Or is temperature going to win and say, volume, you go down? The only way we know is to calculate it and see what happens. It is absolutely 100% possible that, you know what? Volume might not change. What did these two do to each other? They can cancel each other out. That's a possibility too. They could cancel each other out.
You're joking.
No. Now before, we could always tell because there were only two things. There were only two things. And if you did this, this one had to do something else. Now in combined gas laws, we don't get that advantage. Yes, maybe both variables are telling it to go down. Then it has to go down. But one variable could be saying go up. One variable could be saying go down. The only way we do it, we got to work the problems. We got to work the problems. Okay? That is the only way to do it, ladies and gentlemen. Okay? Now, you want to do the problems we've been doing, Boyles, Charles, Gay-Lussac's, by figuring out which variables are changing, which ones are not, and use those individual gas laws, go ahead. You could use this one, and if something doesn't change, put in a 1 for that thing on both sides and then go solve it. Because it doesn't change. Put the same number on both sides. You're going to divide both sides by 10. If it's 10 on the bottom, you're going to do whatever. You could use this one gas law in place of all of the other three that I gave you. And one of the things you're going to find in this unit, ladies and gentlemen, is Rocio's going to solve the problem one way. Farhan's going to solve it another. They both come up with the same answer, even though they use different gas laws and different relationships to get there. It is absolutely fine. Okay? So when you're looking over at your neighbor's test and you're like, oh man, they're doing it much different than me. Who cares? By the way, they probably got a different version of the test anyway, and they're not on the same problem you are. Or at least don't have the same numbers. So, questions, ladies and gentlemen. Tomorrow the fun begins. We talk about combined gas law, and then we get into ideal gas law. Okay? Questions, comments, suggestions that don't involve me leaving the room or killing anyone in it? Okay. Oh, by the way, this lab, the reason I'm giving you till tomorrow to turn it in, if you want a grade higher than a C on this lab, it will be turned in by the end of the day tomorrow, and you will be rewarded for turning it in on time with the opportunity to earn a grade higher than a C. If you do not turn it in by the end of the day tomorrow, the highest grade you can get on this lab will be a C. Questions? Wonderful, wonderful, wonderful. It's cute that you think she's that smart. It really is.
She is that smart. What do you mean? So Cynthia don't even think.
Well, that's
Can't
the
you
more
see her
impressive part
glasses?
is she
She's
doesn't
smart.
she doesn't think she's smart.
Can't you see her glasses?
Who doesn't think they're smart?
You.
Like your hair.
So
Well,
sounds like a me problem.
if you don't have confidence in you, who is ever going to?
I do.
If I take it,
Okay.
I'm gonna start study first.
Thank you, sir. Goodbye, goodbye, goodbye. Doors that way. Use it. Get out. Goodbye. Adios. Arrivederci. Adios. You gotta go. Don't forget what's under your desk, Sophia. Thank you, Angel, for reminding her. I thought it would have been much more fun to leave it, but that's okay.
You can take pictures of yourself.
It's a camera? They even make those nowadays? I thought they were all just on phones.
Well, I need this for Instagram.
Goodbye. 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 Have a good day.
See you maybe tomorrow.
I'll be here.
I won't see you tomorrow.
Yay!